Thank you. So, good afternoon, everyone. It is a pleasure to have you all here. My name is Mauricio Bezerra de Souza Júnior. I am professor of the School of Chemistry at Federal University of Rio de Janeiro. We have been organizing control seminars that are virtual, and they take place every fortnight on Monday afternoons. And we organized it together with the University of Rio Grande do Sul, UFRGS. So today we have the pleasure to have here the group of Radix, especially the president of Elliott Bell. Elliott is currently the program director at Radix. He is focused on advanced solutions for the pulp and paper industry, which is the topic of the presentation. The presentation is entitled Myth versus Reality, How AI and Process Controls are Changing the Pulp and Paper Industry. So Elliott has over 28 of experience in heavy industry, especially in pulp and paper. And previously he held numerous positions with Georgia Pacific. And the most recent one was as Senior Director of Advanced Process Solutions, where he championed the collection and use of business and process data for digital transformation purposes. He is a process control subject matter expert and has extensive experience in management, in process control, and project management. And he holds a Bachelor of Science in Electrical Engineering from Clemson University. Barbara Oliveira will also participate, and Barbara holds the Pulp and Paper Manager position at Radix, focused on digital transformation programs. And she has over 10 years of experience. She is also involved with digital transformation, and she is a chemical engineer who graduated from the Federal University of Santa Catarina. And presently, she is a PhD candidate in process optimization at Universidade de Maringá. So thank you very much, Elliott, for being here. Elliott also presented a talk about 2 years ago to our students at UFRJ, and it is a great pleasure to have Elliott here again. So I will pass the word for Elliott, and at the end of his talk, we will have the session of questions and comments. So Elliott, thank you very much again. I will pass the word for you.
Thank you. Actually, Barbara is going to start us off today.
Yeah, I'm going to start.
Perfect.
Thank you so much. Hello, everyone, and welcome. Thank you for this opportunity, Professor Mauricio, and for all for joining us in this seminar. And as Professor Mauricio said, my name is Barbara Oliveira, and I work for Radix here in Brazil. And at first, I'm going to do a quick overview on our agenda and make a brief introduction about Radix for those who don't know us yet. So we are going to start talking about AI concepts and applications, and then we'll move on to process control part, approaching regulatory controls, short-term and long-term process dynamics, and finally we are going to present the top reason most controls, ML, AI investments fail, based on the experience that we had in projects in pulp and paper industry. And at the end, we will also have a time for interactions and questions. Okay. About Radix, we are a lifelong partner to our clients, supporting sustainability and continuous improvement to achieve Industry 4.0. We have a unique approach to address the digital transformation. We leverage combination of engineering technology, OT, IT, and domain expertise to deliver impactful solutions that drive success, providing complete solution that involves on IT, enterprise-level programs that drive transformation in many areas of the company through intelligence. On the OT domain, we provide solutions and services focused on supporting assets to optimize operations. And in the AT, we develop studies, design, and tools to deliver improvements to pulp and paper projects. We have today more than 1,000 employees with a global presence with successful projects around the world. And in the pulp and paper industry, we have been involved in several digital transformation programs, helping our clients to extract the greatest possible value from existing technologies and also to expand and develop customized system and disruptive projects. And with that, this brief introduction, I will pass this over to Elliott, our greatest expert in AI and process control for pulp and paper industry.
Good afternoon to most, good morning to a few. I will actually turn my camera back off. Unfortunately, earlier during testing, we were seeing a little bit of lag. So by turning my camera off, it gives us a little bit better reception or communication. So just starting off, so many of us have worked in this industry for, the last 25, 30 years or more. And a lot of us, though, don't really feel, or even though we lived the transformation, we can't really remember everything. Some of us have never even really understood how we got to this point. So I wanted to start with a quick review of the road that IIoT started or has traveled down. IIoT being the complete collaboration of all of your data sources into a single system that allows you to do computing and control throughout your single plant or throughout your enterprise, leveraged through the cloud back into your enterprise, right? So when we talk about IoT, it has a path that it's come down. So if you think about the fact that PLCs started in 1968 by Dick Morley, long time ago, 68, that was actually 53 years ago, prior to most of us on this call being born. Then after that, PLCs started really the computerized process of controls, but I will speak more to that later because that's an interesting path on its own. In 1983, Ethernet was standardized. In 89, you had the Hypertext Transfer Protocol, or HTTP, kind of created. In 92, you saw greater connectivity between PLCs and other systems. The interesting thing was I came out of college in 93, so I'm at the heart of that transformation. In 2002, Amazon Web Services launched the first cloud computing, and I want you to remember that date because it will be significant in something I'll show in about 3 slides. Then in 2010, after we got smaller sensors in 2006 and OPC UA started in 2006, in 2010, you started to see the drop in sensor prices, and this drop in sensor prices really begat the period of OEMs and suppliers driving the use of lower cost sensors and driving data to the cloud, which allowed us to do a lot more with various information, various systems, including things like the WhatsApp or apps where you monitor the crowd and then use crowd-based activities to start decision making. Next slide, please, Barbara. So the reason I set that up, the reason we want to talk about the use in the collection of data and the path towards computers is because all of our problems that we are really trying to understand, that we would use AI for, that we would use ML, that we would use process control. In a lot of times, process control started off very simplistic, but as we were able to capture more data, as we were able to start to remove obstacles between processes, we moved from having single base problems to multivariate problems. And so in multivariate problems, you need more data. You need to capture the data, move the data, analyze the data. And as we got to this, we started to be able to remove the obstacles that time creates, move the obstacle that geographical limitations, whether it was the geographical limitation of having 3 plants placed at different places around the world, having 3 suppliers that are in different places around a state, or even having 3 different process areas in the same mill, and those process areas all feeding a centralized component or centralized process, and then we having to understand where the problems were being created in our raw materials that were affecting our final process. We were able to start to understand and remove the historical boundaries. And the more complex the process is, the more having analytical capabilities and data allowed us to be more precise in our answers. And so as we get into new technologies and new capabilities of using the tools of now AI, ML, those technologies actually allow us to even leverage and the correction of even better, more complicated problem sets. So to sum all of that up, it is the winners of tomorrow will be the ones that best leverage new and existing technologies in innovative ways to solve tomorrow's problems. And that's a big sentence, but if you think about what we've learned, we're not using quote unquote absolutely new tools to create new tools. We're using existing tools to create new tools. And in most of the time today, we're using new tools, or we're using existing tools in multifaceted ways that we never used the tools previously, and grouping or layering those tools together is actually how we're creating the new technologies. This actually is the core of what we're doing with AIs and MLs. Next page, please, Barbara. So when you think about artificial intelligence and machine learning, there's some key points that I would like to stress to this group. And I stress them, one, because I haven't really heard, or very seldom have I heard these points made. The first one, machine learning and artificial intelligence is different for the business side or the enterprise solutions than it is for manufacturing solutions. Now, that's not to say that you use different tools, but the focus is actually different. If you think about an enterprise type solution, it is usually a solution that's trying to understand more or less a human-related problem. When are we doing purchasing? How does purchasing behavior change? How do I predict weather? How do I, or the effects of weather? How do I affect a behavior in a group of humans? So it is typically extremely human tendency focused. Whereas when you look at a manufacturing type solution, it is human impacted, but usually very process focused. Now, so just to break this down further, so if I'm looking at enterprise set of solutions, the elusive goal of the AI is to capture the knowledge of a business as the basis of effective decision making. So you're trying to capture the knowledge of the humans in the business and use that to affect decision making as it integrates not with necessarily a single human, but the trend of human decision making. How do we do that? We have to focus on solving the problems by asking the right questions. What tends to be the right question? Well, the right question is the multifaceted question, really depending on what you're trying to solve. So there is no single right question. It is realistically based on what you're trying to do. For as manufacturing solutions, in a manufacturing solution, you're usually trying to understand what are the routine behaviors of the process. The process itself is usually predictable, but there's a set of decays. The most unpredictable part of the process is actually the human engagement with the process. So when you're looking at an AI around manufacturing, there's 5 jobs: sourcing, which is purchasing, the actual act of manufacturing, the need, location, or ability to store the products, the routing the products to and from storage or to and from the warehouse, and then delivering a product, right? So all of those have separate needs, separate requirements, but all of them actually interface with, normally you may interface with a lot of people, but it may be a single person making a decision that will modify the process and can then disrupt the strategy or the effectiveness of an AI or ML. So one of the places that usually AI or ML is really good is the application of autonomous vehicles and autonomous product transport. In those applications, it's usually very, very few, or if any, human interaction. Most people who are running completely autonomous warehouses usually minimize or really try to not allow human traffic in those areas because that is unknown, whereas the behavior of the robots or the behavior of the automated vehicles is very well known and usually very successful. Next slide, Barbara. So with the mindset of AI for a business level, enterprise type AI, enterprise type machine learning is about trends, about business trends, about making the right decision and reducing the risk of a business decision. So I wanted to share this type of an example. So the Chicago Fed, that's Chicago in the US, the Fed National Activity Index. This index on the screen goes from 1970 to 2021. And so this is about the same length of time that the automation life cycle has been going on. It's about the same length of time that I've been here. So if you look, what you'll notice is on the far left side, which is in the start of 1970, you see the different indexes have a lot of variability. It's about a 6-year cycle, but you see the dips and the spikes are very high. And then as you come across in 1990, they decrease some, but they're still very violent. So if you see the dip right after to the right of the 2000 line, you'll notice, go over, Barbara, right about there. No, back to your left some. Right, a little bit more. Right there. That's about 2000, 2002. Remember I said, remember 2002. So in 2002 is when AWS started its cloud service. So note that from about the point where Barbara is, her cursor is, to the right of that, notice that the spikes get considerably smaller. Notice that from that point in 2002, there was a slight recession, and you can see that moved down. After that, notice the spikes, the variability is a lot less. The big drop in 2007, that was the economic turn down at the end of the Bush and the start of the Obama administration. And then right on the far right, you can see the COVID response where you see another turn down. But notice from 2002 on, we've seen a continuous reduction in the variability. And that variability reduction seems to match really well with the start of cloud computing and the point at which we were able to start doing more high-level analytics and deploying AI and ML. Now, if you get to the last few years, so about a little bit more, about that point right there, further to the right, you see extremely small economic variability. Now, at the bottom of this page, the trend on the far left, which is the is sales. That's the sales and sales orders in inventory. Sales orders in inventory are the predominant indication of what manufacturing expects and what manufacturing is seeing. Notice that near the 70s, it was highly volatile, but notice that since the 2007 revolution or 2007 recession, it's been almost not volatile at all. During that time period, this is again a significant indication that the manufacturers and the producers within the US have actually been able to better predict what they expected to have in their sales and then to be able to deliver based on those predictions. Same thing when you look at production and income, which is the red trend, and the blue trend being unemployment in hours. Notice that unemployment has actually been far more stable. Now, that's that's the impact of AI ML over time and computing in general, but specifically the last few years, it's a high level impact of AI and ML in service. Next slide, Barbara. So the question is, why do AI ML fail? Because it's demonstrated that there are applications that are having impact on the world. It's easily demonstrated that having resources help. So machine learning and artificial intelligence are simply tools, right? They're tools for pattern recognition. And in multivariate systems, the more variables and the higher the variability, the more complex the multifaceted solutions have to be. So if you have to have a very complex solution for a complex problem, then the failure modes are kind of repetitive. So here you go. Human engagement is a primary failure mode. And when I say human engagement, there's a few different ways. Again, you have manufacturing compared to an enterprise. So I'm going to speak for manufacturing first or for a second. So with a manufacturing HI or ML application, that application usually has to engage with humans. Usually we either did not build that solution to be completely independent, or the humans have the ability to turn off parts of it, or we don't have a sufficient interface such that the humans understand what the AI or ML is doing, and thus they start to argue with the decisions made by the computer or by the system. Okay, so that's a primary. The second one brings the rest of the process back into the discussion, which is if a AI or ML application fails to address the dynamics due to wearable components. In a business AI ML, there are no wearable components because they're usually looking at the population trends or human trends. In a manufacturing AI or ML, especially if it's in a pulp and paper, steel, any of those systems where the mechanical components will wear out, will plug, can change over time, then you have to have the AI or ML set up to address the dynamics that are part of that process. That's a big one. The next one is quite often the designers of an AI ML solution try to get too large of a solution. So they try to do a single model that encompasses everything. Unfortunately, the more multifaceted a problem is, the more individual pieces you need to build and then integrate into a single solution. i.e., you may have to have multiple models or multiple solution sets in order to address the multifaceted nature of the problem. Okay, the design team fails to include the diversity of experts, i.e., if you're going to address a multifaceted problem, you probably won't find one person that has the complete knowledge to handle every different part of that multifaceted solution. So you have to have a diversity of experts in order to really address the communication and the knowledge base of the process or the knowledge base of the company. The sustainability and integration, staff and training and support. Do you have the right people? Do you have the right communication? Do you have the right meeting time to do a continuous real-time optimization of the model? Lastly, especially for a manufacturing AI or ML, and this comes from the support and staff training, are you going back to your models and adjusting those for process changes, whether it's a process equipment change or whether someone decides to fundamentally change a part of the process? Those all need to be picked up and reinstituted in the model, or the model needs to be smart enough, or models need to be smart enough to collect those changes and integrate them such that it has an accurate idea of what's going on. Because what will happen in any of these bottom three, the bottom three usually causes the first bullet point to become the most important. If the operators or the humans that are engaging with the model start to think that the model is not correct, they will turn it off. Okay, next slide, Barbara. So that ends the AI, the AI focus. So process controls. So humans historically have been designed into the manufacturing process, right? If you think about it, we've always had a mindset that we were going to install the human either to save the day or to make a decision, but we generally always design humans into our process control or into our process. So manufacturers today are slowly trying to reduce the human dependence. The reason for this are multiple, but at the top of it is baby boomers are retiring and we just don't have as many people in manufacturing as we used to. Because of that and other things, we are trying to design our systems now to be less reliable. But if I look at the key components of a process control system, the first one is the operators. And a true process control expert has to design his process control system to work with the operators. Next comes your field measurement devices, your controllers, your field control components, then your human machine interfaces, your DCS screens, your alarms. And then what a lot of people don't necessarily understand is a process control expert has to be knowledgeable of the manufacturing process equipment. They need to understand the process, how the process is sized, how the equipment is sized, and what the functionality of that equipment is. After that part, the last, to me, most significant piece of being a process control engineer is you have to understand data capture, data management, and data analytics. Data analytics provides the ability to understand how well your system is running. If you can't capture the data, you'll never be successful running the analytics on it. If you don't understand data management, you will probably create a mess that makes doing data analytics very difficult. Okay, next slide, Barbara. I think you skipped one. Or did you? Okay, go for it. Thanks. Okay. Process controls, for me, is defined as the automated control of a manufacturing process. I think we all know that this is used extensively in oil refining, pulp and paper, chemical processes, electrical utilities, generation, food and beverage. You know, heavy industry uses regulated, automated process controls. Process controls, as I've spoken about, has been implemented over the last 50 years. And one of the things that I would share is we're actually in our 5th revolution of process controls. I know a lot of people have heard about Industry 4.0 and a lot of other things, but if you think about just process controls, in a little bit over 50 years, we've traveled from push buttons and 100% manual valves to first pneumatic controls, where you had pneumatic single loop controllers, you had pneumatic charts, you had, just pneumatic controls, you had some levers. Then we went to single loop electrical controls, then Unix-based DCSs or distributive controls. In the late 80s, early 90s, we started Windows-based DCS controls. And in the last 15 years, we've really gotten into IoT and data-driven controls around smart devices, advanced process controls, ML, AI controls. So we're really in our 5th generation of process controls. And through that 5 generations of controls, the most significant part has been we have always been fighting variability, but we've not always been paying attention to dynamics. And the reason that I stress the 2 of those is a lot of times we will build controls around a single point of variability. We will tune a loop for one specific gain cycle, or we will tune a process for a specific point in the process, kind of ignoring the rest of the dynamics that happen. Okay, next slide. So when you look at dynamics, you have short-term and long-term dynamics. Short-term dynamics, single loops. It starts with having controls that run in manual. It could be caused by measurement issues. It could be caused by individual loop tunings. It could be caused by a single point of tuning in a highly dynamic process. Let's say you have a process that you run 5 different grades, but you really only have the loop tuned for a single grade. Local process dynamics are generally longer term, but they may be a process dynamic where you have multiple loops that are run in a cascaded scheme, and one or more of those loops creates a long-term dynamic that the entire process is subjugated to. So you see a continuous swing through the process, but it's really just that process. So this is unfortunately quite normal in systems where you have cascaded loops. It's normal where you have a process where there's a gain change due to a rate change. It's normal where you see grade changes, especially if the grade then requires either a rate change or it requires a concentration or a consistency change. It shows up in mechanical changes over the lifespan of wearable parts, because usually if you have something like a refiner or a pump that wears out over its time, that pump will create less potential energy when it's running as it wears, and therefore the gains that were originally put in place are not sufficient. I'll talk about steam header controls in a second. And then lastly, especially in pulp and paper, you can see final quality swings. And the final quality swing may be a swing that can last over 12. I've seen some that go as long as 24 hours in a very slow, gradual change due to either tank levels or due to a quality change that's happening in the back of the process, working its way forward. Next slide, please, Barbara. So real quick, so drum level and 3-element drum level. The figure on the right is a 3-element drum level control. The figure on the left is a single element drum level control. I wanted to show these compared to each other because in simplistic terms, they would be controlling the same thing. In simplistic terms, they're both controlling drum level. In a facility where you have a single user or a boiler that is so large that it can easily sustain the facility, you can usually run a single element control because there's nothing creating the disturbance. In a facility where you have multiple users pulling on the steam header, that can cause disturbances, that can cause variability, then you need a lot more complex control scheme in order to drive stability or to reduce variability. In short, in that case, you need some feed forward that goes into the system to help address the variability. In that case, in both cases, we would want to control feed water flow that's going to the drum. In a 3-element drum level control, though, you would have to measure your drum level control, or you would have to measure your drum level, excuse me. And in measuring your drum level, you would also have to include a density compensation for your drum level measurement that addresses the density, because that drum level is a 3-phase system on its own. Once you get that, you would want to measure the steam leaving the drum and then apply the steam leaving the drum as a feed forward signal that helps in adjusting the control to your feed water flow coming into the drum. So again, the more complicated the system, the higher number of variables, the higher number of variability, or higher the amount of variability, the more complicated your solution has to be. Next slide, please, Barbara. So from a drum level control to a steam header control. So of course, the drum levels are part of the boilers. When you think about steam headers, the most interesting part of a steam header is it is actually designed to have multiple gains. If you think about how the gain of a header works, the heat in the steam creates the potential energy. The rate that steam is being pulled out of the header creates your flow, and that then impacts the amount of potential energy that you have to keep in the header. So what happens if the header goes to a low pressure situation at the same flow rate? Well, you just had a substantial change in how much energy you have in the header. Therefore, you're going to need a different reaction of your valves. Same thing if your header is at its normal pressure, and at its normal pressure, you see a flow decrease. Once you see that flow decrease at its normal pressure, you require a different response out of your control valves. Otherwise, it's going to overreact. So when you look at something like a complicated steam header system, you have to have an adaptive gain to coordinate responses across multiple headers. If you don't, what you're having to do is you're forcing the operators to have to interact with the system in order to try to sustain stability. In most cases, in that situation, the operator is reacting in a lag. They're only going to be reacting once everything is updated, and therefore they make the entire process of trying to stabilize a system like this more complicated, or they make it worse. So in this situation, advanced process controls and AI ML to help stabilize the steam header has been very successful over time. Next slide, Barbara. It's all you.
Okay. So, and finally, I would like to bring a poetic inspiration that I believe that has a lot to do with the theme of this seminar. Because when we are faced into two or more possibilities, which road to take? And this is the poem, The Road Not Taken by Robert Frost. Two roads diverge in a yellow wood, and sorry I could not travel both, and be one traveler. Long I stood and looked down one as far as I could, to where it bent in the undergrowth. Then I took the other, as just as fair, and having perhaps the better claim because it was grassy and wanted wear. Though as for that the passing there had warned them really about the same. And both that morning equally lay in leaves no step had trodden back, Oh, I kept the first for another day. Yet knowing how a way leads on the way, I doubted if I should ever come back. I shall be telling this with a sigh. Somewhere, ages and ages hence, two roads diverge in a wood and I took the one less traveled by, and that has made all the difference. And I believe that in many of the main challenge in our life, we have to choose the road not taken, for it is by launching into the unknown that the main discoveries in our human history were made. And with that, I pass over to you, Elliott, to your final considerations. You are on mute.
Me and the mute button, I swear. I like to say thank you to everyone for your time and this opportunity to speak to you. I will admit that's actually one of my favorite poems. And I would say this, when you think about the road not taken and process controls is both an art and a science. There are some people who can do absolutely great things by doing what is standard. And there are some people who can do absolutely great things by doing things that are completely innovative. There is no perfect answer. There is no single right way. There is just opportunity to progress. And so I would tell you, I take the road less traveled by, and I try to make a difference. Thank you.
Thank you, Elliott. Thank you all.
Thank you, Elliott. Thank you, Barbara, for the very nice presentation and motivating presentation. Also, we have people here from the academia and also from industry. And I think that especially the students are really very interested in applying the knowledge that they gain at the university to the pulp and paper industry, for example. So it's very much interesting. And I would like to say that we will start the questions and comments now. So maybe we could do the following. You could please put your name in the chat so that I can address the questions to you, okay? We are very interested to hear the audience. And as I said, people from different industries, as I said as I saw in the list of guests. And I will pass the word for Filippo Soares. Filippo is one of our PhD students. Please, Filippo, if you can open your camera, Filippo.
Good afternoon, Mr. Bell, Ms. Oliveira. It was a really interesting presentation. I have a question. You mentioned that trying to infer the dynamics are a more interesting difficulty, a more interesting challenge. One thing I found about trying to apply machine learning to dynamic process is that it's really hard to actually get a good result of it. There's not many data about the dynamics. Sometimes the answer depends on the states that are not observable. Sometimes the inputs we have will match different outputs depending on the internal states that sometimes are not observable. So do you have, and sometimes they're not a lot of data. Sometimes the operators try to keep the process on the steady state and they avoid dynamics as much as possible. I would like to say, do you have any tips about applying machine learning to dynamic process?
Yeah, so it's interesting because you hit 2 or 3 things in your question. So one is, of course, one of the first slides I made was about gathering data and the ability to gather more data. So if you start to limit the data, then that becomes a problem. But here's the bigger issue. It's kind of like a subroutine. When you look at certain dynamic situations, you're looking at an very isolated situation, and you have to actually treat it like that. So sometimes you may pick up a dynamic change, a step change, or an outlier. And with that, you almost have to configure it as an interrupt, more so than trying to let the machine learning find it every time, especially where you have limited data. But what you definitely have to do is you have to, in a situation of low data, you have to break out that dynamic situation and have it identified as almost a subroutine. Okay, if I see this, I know something's happening. Now, that doesn't mean that you're going to pick everything up ahead of time. Sometimes you will only pick them up once you've seen them. But once you've seen it, that's where you have to, through your support system, build it back into your process.
I see.
Okay.
Thank you very much for your answer.
Yes. Yes, I'd like to invite the audience to make comments. Professor Ajimiro has raised his hand. Yes, Ajimiro, please.
Yeah, thanks, Mauricio. Well, can you hear me well?
Yes.
Yes, okay. Okay, Mr. Bert, thank you for the presentation and what your thoughts about the AI and L for the process control community. But do you really think that the process control is in its 5th revolution when talking about chemical industry? I mean that about the cyber physics device plus cognitive systems. What I mean by a 5th revolution, and I don't know, it's the same as you mentioned. So do you really think that you are in that situation now?
Yeah. So I've had either the pleasure or the penalty of working in mills from everything from my first PLC was what they call the Allen Bradley PLC 3. So I've worked on PLC system 3s. I've worked on the 5 series control logics into where we are now, which is just a different version of control logics. I've worked on Unix-based DCS systems. I've worked in the early Windows-based DCS systems. And now, even as we move towards cloud-capable DCS systems. But so if you think about PLCs were generated by moving from relay-based controls into a PLC-based controls. DCS were a function of taking single loop controllers and moving from single loop to distributed controllers, right? And so when you think about what was there with pneumatics, when you had pneumatics, you were absolutely limited to a geographical region, right? Because you could not go too far beyond the limits of the hoses that pneumatics ran on. Once we got beyond that, we had electrical single loop controllers that were also isolated. In our first approach to DCS, we would isolate the DCS equipment to the same geographical limitations that we would isolate our single loop controllers. Well, in today's world, even though some of the mills that are behind will still isolate to geographical regions, most companies have stopped isolating their controls to a single region. And now most of the producers are building controls that are either networked or that are cloud-based so that they're not isolated to a region. So that actually has completely opened up the networking back to that IoT mindset, where I can take an individual data point and easily move that individual data point wherever I need to within my system. So for me, before joining Radix, I have done things like we operated a set of evaporators from 600 miles away. So we were operating a set of evaporators that physically sat in Florida from Atlanta. We have supported advanced process controls from around the world. We have individuals from Radix that supported advanced process controls, making changes in DCS, making changes in the APCs from Rio as far as Toledo, Oregon, or other parts of the US. So would I say everyone is in that fifth revolution? No. Would I say the technology and the mindset that is currently being employed has entered into the fifth revolution? Yes.
But for me, this seems to be the fourth revolution yet, not the fifth.
Well, but that's where the vast majority of people are. That's not where the mindset is. Because if you think about what is our predominant mindset over time, it's always been something has limited us, right? So could you go back to that slide, Barbara? It is the change for the process control one. You just passed it. Go one more. It was the second, one more. So the mindset behind pneumatic controls, how you deployed a pneumatic control was actually different than how you deployed electrical single loop controllers. How you had to deploy a Unix-based DCS is actually different than how you deploy a Windows-based DCS. So now when you think about those are the ones that are the top four. So now in this fifth one, and I know people want to say the fourth industrial revolution, but in the fifth controls revolution, it is very much a mindset change from Windows-based DCS that are local to a site to a data-driven analytics, smart devices, ML AI process control system. That's why I say the fifth.
Okay, understood. My concept that also includes the cognitive systems inside of the smart device and human interaction with. So it's a definition.
I tell you what, I would love to follow up more. I know we have 20 minutes left, but I will reach back out to you because I would love to discuss that more.
That's right. Okay, thank you very much.
Thank you, Ajimiro. Elliott, Gustavo Souza has written a question. And he is asking you, in fact, to describe an example of the pulp and paper industry, mainly regarding the craft process, in terms of AI, ML applications. You see that render a good cost-benefit relation.
So here's some really good ones, but they are also difficult. So if you think about especially the craft process has a product and a liquor from the craft is not the product. It's a byproduct, right? And soap from the craft process is a byproduct. But if you think about how most facilities are set up, if you're just looking at craft, you want the fiber at a certain kappa, and that's what the paper makers are really looking at. And if they get really specific, they want fiber at a certain kappa with minimal conductivity. Well, the problem is if you overwash, then you're sending more water to your liquor recovery system than you absolutely need to. And there's a cost to that. So a great AI application is one that looks at your chemical cost on your paper machine compared to your evaporation cost in your evaporator liquor system, and then adjust the washing dilution factor of your washers to optimize to the greatest benefit of the meal. Because like here during the winter, when your fuels change to produce steam, or if your evaporators or your recovery boiler is running at a lower efficiency than normal, then that cost of water changes as you send that water to the utility area. Meanwhile, someone has to consider what's that additional cost to add chemicals on the paper machine, or whether or not you slow the paper machines down. So there are a lot of applications where you can use AI to really help a paper, especially the back end of the paper mill. Similarly, you can look at your caustic area and how the caustic area is performing compared to the cost of running the lime kiln.
But yes, Gustavo is thanking you for the answer. Elliott, are people using in a routine basis, for example, neural networks to predict the behavior of the kappa number already? Is it common now, or is it still, yes? Because I'm aware Radix in the past developed some works for the prediction of the kappa number using neural networks, for example.
The answer is yes and no. So there are people our age, my age, your age, that have used neural networks for a while, and they will still build them into their solution. There are other engineers, other experts that are almost like the social media presence, where they want to build in whatever's new. And so they may circle back to a neural network, but they may do 5 or 6 different things just trying to use the new technology present. So it's kind of, yes, you can find them, but you may also find 4 or 5 other solutions.
Yes, that's interesting, because I was thinking about asking you something related to this, because this kind of, you see, yesterday I was talking to my son. He is a 21st century boy. And he was telling me, "Oh, father, this is very nice because you have experienced the change you see, in the technology because of the internet. You had that experience." And I was thinking, if the pulp and paper industry is already having this kind of change in the behavior of the engineers that were already grown with the presence of internet, while some of them, you see, experienced that change. They began their careers together with the internet, but some of them are being born now in this century with the internet or digital world completely present. Are you feeling already this difference? Your comment made say that yes, some of them have so many, you see, tools that they are aware that they can use, that they trying to experience everything. Do you have more comments about this difference between people that were born with the internet in the world and others that had to adapt themselves? I don't know if yes. Mm-hmm.
Well, so here's the good, bad, and there's opportunity and there's problems there. The opportunities are, when I started, you didn't have the opportunity to work remotely. We just did not have the capability. You know, the best you could do was, if you were lucky, you may have had a modem that someone could dial in through a modem and dial into a single computer usually. You know, and that was even still far between and a security risk even at that point. In today's world, it is quite common in many, many mills that you have 100% remote access. And that 100% remote access really helps in maintenance and in support. We do see a lot of, you know, in data collection, in order to build advanced controls, the internet and the collective data historians have been great, because now, where historically individual mills were individual kingdoms, and you know, you could look at one kingdom at a time, and if you were working on kingdom A, you couldn't really work on kingdom B, and it was just difficult. Well, now you can take multiple mills and take those multiple mills and put them all on a dashboard together, or you could use, you know, analytics to quickly baseline multiple mills and be able to identify who's the highest performer and use that high performer to compare against your other mills. So the accessibility to data has been absolutely great. It is just a game changer in itself. Likewise, the accessibility to look at a program in one facility and then take that program and deploy it in a different facility, having never been to either facility, is just absolutely game changing. So there are a lot of things that today's engineers are capable of deploying that will allow them to work from home, and they'll never really understand some of the struggles that were previously in existence.
I would like to pose something for the audience, because if there are students that are curious about Radix or Radix, you can also make some questions to Elliott and Barbara about the company, if the students have any curiosity. Yes, Ajimiro is not a student. That's, yes.
Yeah, I have another question to Elliott.
Yes, Ajimiro, please.
A technical question about
yes, of course.
If Elliott would talk more about your experience in the pulp and paper industry regarding to the AI, ML for adaptivity, regarding to the short, long-term dynamics, and also the machine changes its parameters and behaviors, and how the AI and ML are doing well in with this problem.
The biggest opportunity is in the knowledge of the architect, right? So, and I put in there about the problems of dynamics, the problems of how you architect the solution. So I'll give a couple of quick examples. Years ago, I worked with a company. They came in and they said, hey, you know, we're really knowledgeable. We know what we're doing. We can help you figure out strength properties on the machine. And what they did was to say, we're just going to go do one large model, and we're going to model the strength and see which parameters are impacting strength. And what they got was a model that virtually said, we don't know. And the reason that they got that answer is because a paper machine is usually somewhere between 6 and 13 sections. And any of those sections can impact strength. Now, some impact strength a lot more than others, but as you have draw between the sections, you can pull a sheet apart. As you reheat, redry, or re-wet, re-dry a sheet, you can impact the strength. How you refine the fiber before you introduce the fiber to the machine can impact the strength. And so they did not have the individualized models, or shall I say compartmentalized models, in order to be successful. Now, I went to a meeting with the same firm last week, and so now 6 years later, they have an extremely impressive model, but it took them years to figure out that they had to separate into a lot smaller pieces and then integrate those pieces almost in a reflection of the mill or of the machine.
Yeah, but they put more knowledge inside of each piece of model, probably.
Exactly.
Yeah, good answer. Yeah, thank you.
Okay, so I think that I will ask the audience if there is any question, an additional question or comment, I would like also to announce, yes, before that, I pass the word for Emmanuel, but before I would like to announce our next seminar that will happen in November, because we have a holiday that the next fortnight. So the next seminar will be in November, and it will be given by Luiz Eduardo Ganin Rubião. It was a coincidence in the program because Rubião was the founder of, together with other partners, of Radix, and also from Kentech, and we will talk about the challenges of entrepreneurship. So it will be a very interesting talk, and I would like to invite you from now. Emmanuel, do you want to make the question yourself? I can open the mic for you. Do you? Because he has written the question. So if you would like to talk. No? So I can read it here. He says that he works in a tissue paper company, and they have tried to train a model to predict a variable using historical process data, expecting that the variability of the process would be enough to explain this variable. But they didn't have success on it. So he is asking how to deal with a dynamic that is apparently random, or it is not statistically significant.
So two things. Can you tell me what the variable was?
Yes, Emmanuel, please. Softness.
So that whole story that I just told you, refer to that. So when you're looking at softness, if you're trying to look at softness, but you're looking at the entire machine, you're really, when you say it was not significantly relevant, the problem is when you look at that entire machine and you take all of the parameters for the machine and you want to get to softness, you really have to lower your expectations of your R-squared value. Because if you go into it looking for 85, 90 R-squared value to think that that's significant, you're actually taking the wrong mindset. When you look across your machine and you look across all of the different sections and all of the different impacts, your R-squared value that shows significance is actually far smaller, just because now you're not looking for a first order relationship. You're actually looking for probably what is maybe even a fifth or sixth order relationship. So you either have to start with some of the known impacts, or you just have to reduce what you're thinking is a significant indication based on your R-squared value. But to get really good, you're going to have to create, and I'll do my shameless plug because I hadn't done it. Give us a call. We would be more than happy to help you with that. And our information is up there. But what it comes down to is you're going to need more than one model in order to model it correctly.
Thank you, Elliott, and thank you, Emmanuel. So, Elliott, I would like to thank you very much for your presentation and for being open to come and talk to us again. And it is very good to learn all your experience as an expert in the pulp and paper industry. And I'm also very glad to meet Barbara again and people from Radix. We also are very much in contact and collaborating. So I'd like to thank also, I don't know, I think he is not here, but he is always together helping us. Flavio Valtz also. Thank you very much. So I will pass the word for you, Elliott, and for Barbara for your last words today, and so that we can end the seminar for today. Thank you very much.
Thank you. Barbara?
Okay, I just want to say that it was a pleasure for being here today with you, all of you, talking about these very important topics about AI and control process for our pulp paper industry. And we are at your disposal for future discussions. Our contacts is here in the slide deck. And thank you very much, Professor Mauricio and Elliott Bell also for this meeting.
I would also like to say thank you again for having us. As I said, always fun. To Barbara's point, we are definitely here for discussions, for further discussions. Please feel free to reach out. Thank you.
Thank you, Elliott. Thank you all. Thank you all the audience also. We will be here, as I said, for the next seminar in November, the 8th. So see you then. Thank you very much. Thank you, everyone. I don't know if Janeiro is here and can also say something if he wants. Okay.
So just thank you, Elliott and Barbara for this talk. Hope to see you again here.
Thank you. I will stop recording. And thank you.
Thanks, everyone. Bye-bye.
Bye,
Thank you.
Elliott. Thank you very much.